Let's talk about magnetic field force and the related torque. We know that when charges are moving in the magnetic field, they're going to experience magnetic field force. Actually, when charges are not moving inside the magnetic field, they are not going to feel any magnetic force. That's different from the electrical field. In the electrical field, you have force due to the electrical field equal to the charge multiplied the E field, no matter your charge is moving or not. And the magnetic field created force on charges is going to be equal to the charge multiply the velocity vector cross product B vector. So if your velocity is 0, you do not receive any force. This equation is used to calculate the forces applied on charges while it is moving inside the magnetic field. Similarly, if you have a wire and you have a current going through the wire, the wire is going to receive a force. And that force is proportional to how large the current is, how long the wire is, and how strong the B field is. And again, the direction of the force is going to be the cross product of the current direction multiply the current direction cross product the B field direction. And let's look at the right-hand rule number 3, or right-hand rule number 1, which says when we have current, when we have A and B cross product, notice that this camera did something tricky so that you can see all the words in the right direction, but this is my right hand, even though it may look to you like a left hand. This is my right hand. So I'm going to align my 4 fingers first along A, and then bend my 4 fingers toward the direction of B. And then my thumb is going to tell you the direction of the product A cross B. And actually, if you have B cross A, you're going to get the opposite result. If we have B cross A, we are going to first align our 4 fingers along B, and then bend toward A. And in that case, B cross A, we are going to get something in the opposite direction. So keep in mind right-hand rule number 1, 4 fingers along A, bend toward B, gives you the result of A cross B. And then because of that, we know the resulted magnetic force is going to be perpendicular to the velocity of the charge, also perpendicular to the B field. Let's try a few cases here. When we have a B field into the page all over the place, and now we have a positive charge moving in this direction, so the direction of the force would be V cross B. Align your 4 fingers with V. And then now you have to bend into the page toward the B direction, V cross B, and you receive a force in this direction for this charge, and that's positive charge. And then your positive charge moving in this direction is going to receive a force in the direction of V cross B. Bend your 4 fingers toward B field direction into the page, and that is your force. So this is your force, and that's your force. And be careful, Q also plays a role. If you have a negative charge moving in this direction, your V cross B is upward. However, because it's a negative charge, the force is going to be reversed comparing to V cross B. So in this case, even though V cross B is upward, the force actually is downward. That's the force. Okay? So then if we look at this case, when we have current going through this way, and this is a piece of wire carrying current going this way, the rest of the circuit is not shown. Just looking at this piece, it is going to receive a force in the direction of IL. L is in the direction of the current. L cross B. Align your 4 fingers with current, bend toward the B field direction, and this entire wire is receiving a force to this direction. That's your force. Okay? Now if you have a positive charge and it is moving in this B field, when it enters the B field like this, it's going to receive a force toward that direction, as we just figured out. And then that's going to change the direction of the motion, and then it's going to bend the trace this way, And then you can imagine everywhere where you are receiving a force perpendicular to your velocity. A force perpendicular to your velocity is not going to change your speed, but it is going to always, when you're pointing toward the center, and provide you the centripetal force to make you maintain a circular loop. In that case, we can set up an equation QV cross B when V and B are perpendicular to each other. V cross B equals to the value of V multiplied B, the magnitude of force equal to that, which is providing you the centripetal force, which is equal to the mass of the particle, velocity square over R. By doing this, we can solve anything. If we know B, Q, V, we can find out the radius of the cube orbit. If we know R and V and B, we can measure the charge of the particle, things like those. Okay, and also you know that when it is rotating like that, you can have angular frequency equal to 2 pi over the one period of time for you to finish. And the period of time is equal to 2 pi r over the speed v. That's how long you finish one cycle. And later you're going to notice how this omega or t is determined by the magnetic field and the Q and the M, stuff like those. Now, what happens if we have a loop of current, which has not only one segment of a wire, but 4 parts, a rectangular loop? Now let's see. When the B field is in this direction, now we have current going this way, and the force it's going to experience is going to be align your forefingers with I, and then bend toward the B direction. Okay, I bend toward B. So this side of the wire is going to receive a force into the page. Something is pushing the side of the wire into the page. Reversely, if you have a current going down in this side, you align your forefingers with I, and then you have to bend your forefingers toward the B, and then the sum gives you the direction of the force, which is out of page. So what's going to happen to this coil? It has one side being pushed into the page, it has another side being pushed out of page, and then this is going to rotate. And you may wonder what happens to the this part of the current here. Notice that if your current and the B are in the same direction, the cross product is 0. This part and the bottom part, they do not receive force. And this coil, when it is parallel to the B field tries to rotate it and align it in this direction. Okay, so let's see what happens after this coil is rotated by 90 degrees. And now it's in this direction. Okay, so this current I going downward, and then going downward, align your forefingers along I, bend toward the B. This coil still, this side still receive a force coming out of page, which is pushing toward me, pulling toward me, and this is a three-dimensional drawing pulling toward me. Out of page looks like this, and the other side of the coil has current going this way, bend toward the B, you get a force pulling in the opposite direction like that. Okay, now you have this coil being rotated from the initial position by 90 degrees, and now you still receive force, but the forces are going to pull you in or pull you out. These two forces are not going to rotate you anymore. It's going to cancel out, and that's the equilibrium position, meaning a coil or a loop of current, when in the magnetic field, it tends to align itself, tends to rotate so that it can align itself in a way the normal direction is in the same direction as the B field. And the normal direction of this loop provides another concept of magnetic moment. A magnetic moment of any shape, or rectangular, circular shape, any shape of looping current is equal to the current itself multiply the area of the loop, and it has a direction in the direction of the normal direction. For such a loop, the normal direction is into the page is like that. Okay, so what happens when you put such a loop or such a magnetic moment inside the B field toward that direction? So you are going to receive a torque which is equal to the M direction cross product B, a torque downward. What does a torque downward mean? A torque downward means it's going to rotate this way, this way. That's why this coil is going to rotate like that, and it's going to prefer this position when the torque is equal to 0. Okay, so charge in moving in B field receive forces, and when the velocity is perpendicular to the B field direction, it's going to form circular motion. And the wires carrying current receive forces in the B field. We can figure the direction of the force. And if we have a loop of current, it receives the forces in maybe all the other side of the wires. However, they combine together, they may provide you a torque. And this torque tends to rotate the coil so that the coil's normal direction align with the external B field direction. And that's the direction when it is balanced and the torque equal to 0. And this reminds us the other right-hand rule. So we know already the right-hand rule number 2 says that if you have a current this way, you align your thumb of right hand with the current, your 4 fingers bend along the direction of B field. Similarly, now if I do not have a straight current, I have a looping current. And this looping current is going to generate a B field. And that's actually pretty complicated. This looping current is going to generate a B field along the center axis in that direction, and around it, it's going to bend like that, like that. That's B field, that's B field. And then it's going to come in like that. And then outside, it's going to bend, because the B field, they form loops. That's the real B field created by this looping current. However, the right-hand rule is going to tell you the B field direction inside the loop, at the center of the loop. So if you have a looping current, what you do is you align your 4 fingers along this loop, and your thumb is going to be pointing toward the B field direction that way. Okay, so let's try. If we have a looping current like this, and this is going to give us a B field looping this way, the current looping this way, align my 4 fingers along current, and then we are getting a B field out of page coming toward me this way. And then if we have a current clockwise going this way and align our 4 fingers with that current, we are, this is out of page coming toward me. And this one, when we have a current looping clockwise, we are getting a B field into the page going away from me. That's the current created by this loop. Okay, and the direction of your magnetic moment is the same direction as that. So when we have a B field like this, it tries to rotate this guy that way, and it tries to rotate this guy this way, so that those normal direction of the B field inside the loop are going to try to align with the external B field if we have an external B field in that direction.